Let's say that you are in charge of our fancy French museum and you've recently suffered a burglary, which is very unfortunate.
Le montre en train de s'emparer de pièces précieuses du musée. La police, déjà mobilisée, est en pleine enquête pour éclaircir ce scandale.
So you have gone to the president and you've told him, we've suffered this burglary, you've offered your resignation, but he's actually refused it and instead demanded that you draft a new security plan to monitor every square inch of the facility moving forward. So let's just survey the problem. For many art museums and many buildings indeed, the layout is actually quite a bit confusing, but there's going to be some simplifying assumptions that we can make to make our lives here a little bit easier. So the first thing we're going to do is just assume that all of the walls are straight lines. There's no curves, there's no circular rooms, they are just straight lines. Now another thing we're going to assume is that we basically just have polygons. So this is an example of a polygon. It's all just one long line. They're all straight. There's nothing inside, there's nothing outside, there's nothing coming in, there's no openings. And there's also no internal walls. Now you might say that, in a real gallery, you might have internal walls, but to keep things simple in this case, we're gonna have just a polygon. There is a clear inside and there is a clear outside of everything else. So we could take this pretty standard shape. You can definitely imagine an art gallery that looks a bit like this. And we can start by coloring in each of the corners, or in math speak, each of the vertices, the singular that being each vertex. In this case, there are 28 vertices. Again, these are just corners, really. So if we place a guard at one corner, they can see actually quite a lot because we've chosen a good corner, perhaps. So the guard here sees basically everything in this blue area. And for the purposes of this question, we are indeed assuming that the only place you can put guards is at a vertex. Of course, in the real world, you can station guards along the walls. You can mount a camera on the ceiling, which can probably have a better vantage point than a guard who might be blocked by walls or crowds. But for the purposes of this question, again, we're going to assume that we can only place guards at the vertices, and that assumption will actually come in useful later, you'll see. So if you were just given this one room to staff out manually, you could probably easily say that, these 3 guards cover a good amount of the room, though of course there's going to be some blind spots. So here, for example, you can definitely imagine putting a guard here who's able to just, turn his head about at 270 degrees to monitor this entire area. You can definitely place someone to cover this area as well. But we don't want to do this manually for the millions of rooms that, might occupy an entire museum complex or a national museum system. And so another concern is that our president is actually having some trouble getting his budget passed through the National Assembly. So the Assembly is pretty raucous. They don't want to give him, all the money for infinite stuff. So he wants you to give him a reasonable number that will be 100% at least the bare minimum, or at least it will be enough. So he's not going to have to vote you later funding if it turns out he gave you too few guards, but you also can't ask for an infinite number of guards. You can't ask to be given, enough guards to put one on every single corner, because that's going to be a bit of a strain for the state finances, which are not having the greatest time right now. So he asks you, how many guards do you need at most? And you do not know, because you do not have the time to go through every single room in every single museum that you are in charge of. So luckily, a fellow named Václav, who originally from Czechoslovakia has since moved to Canada and the US, he says he can give you a good enough number. So it may not be the most efficient possible number, it may not be the smallest possible number, but it will always be good enough, and it will be a reasonably small enough number. You say, that's wonderful. You ask him how, and he says you can do it through triangles. So if we return to our basic shape with all of our vertices mapped out, we can observe that it's pretty easy to cut the entire shape into nothing but triangles. And the fact this is possible for any polygon in this specific case, because it's pretty orthogonal, that is, we have just right angles, we don't have any, weird bendy shapes or anything like that, we don't have any weird spikes, we can cut this into a lot of triangles, of which many are right triangles. And what we can do is we can observe that if you have, someone placed at this vertex here, they can definitely see everything that is in a triangle of which they are part. So if we place a guard right here at this vertex, they can see every triangle that they basically touch. See the same thing here and the same thing here. And what we can do is we can say that we've divided our entire shape into vertices, and we can color in those vertices. We can pick 3 colors so that every single triangle will always have just one blue vertex, one red vertex, and one yellow vertex. And we can see it's actually pretty easy to devise a coloring scheme such that that is true across the entire polygon. So if we place someone at every single blue vertex, what we will have done is we will have covered every triangle, because every single triangle has a blue vertex. And if we cover every single triangle, we are covering the entire museum, because of course the entire museum is made out of triangles. So we can see here that this fella here covers all of this space because he's part of all of these triangles. This fella here covers this space, this fella here covers these spaces, and so forth. Now you might observe that this is not the most efficient possible arrangement. So for example, the fella up here who guards just this one triangle area, his job could definitely be done by this guy. He can definitely see this area. The thing is that knowing that for sure requires us to come in and make a visual inspection, and we don't want to have to do that. Again, we could also observe that this guy here, who only guards this one triangle, he could also be made redundant. But the beauty of this formula, which by the way also works if you place someone at only the yellow positions, just look like this, you need 9 guards for this as well, to place someone at only the red positions. In this specific coloring scheme, it turns out there's 10 red positions, so this is slightly less efficient. But the beauty of doing guards at every single vertex of a given color is that it's always going to work. We won't have to do any visual inspection. So here I don't have to color in these triangles to see, can this guy hypothetically see all the way into this triangle even though he's not directly touching it or anything like that. So again, we have 28 vertices, and we know that because a triangle is going to have one of each color, there's going to be about 28 over 3 numbers of red, blue, and yellow vertices each. Now we can just round this number down because, as we saw, red requires 10 guards, but we can put 9 guards just as easily at all of the blue or all of the yellow vertices. So what this symbol here, this notation means, is just to take the floor of the value inside. So in this case, 28 over 3 is 9.333 repeating, and to take the floor of that, we basically just round it down. So we say that the floor of 28 over 3 is 9, and in fact we can do this for any shape, any polygon at least, where n is the number of vertices. Again, the number of vertices here is 28, so in this case n equals 28. So Václav tells you that 9 guards, that is the floor of n over 3, in these sets with the smaller amount of vertices. In this case, he's actually made an error here. This should actually be the blue or the yellow vertices, because if you recall, the red guard set, that actually takes 10, whereas the blue and the yellow, they actually take 9. So what he should be saying here is that 9 guards in the blue or the yellow sets of vertices is enough to guarantee that you will cover the museum. Now, is it possible to do less, you might ask? Can I get away with, fewer than 9 guards? Can I do 8 guards? Can I do 7 guards? Well, probably, at least in this case. Again, like we pointed out, this guard can be eliminated because this guy can do his job. This guard could be eliminated because this guy can do his job. And you might even guess that this guy here could also probably be eliminated because this guy can also monitor his entire area. So this is a valid configuration with just 7 guards, where we have removed 2 redundant guards. So again, we will have to remember that n over 3, that is a floor. We know that number will always be enough, and there may be more efficient ways to canvas the entire museum, but we don't know for sure without doing a visual manual inspection. And the beauty of this floor of n over 3 formula is that it will always work. You won't have to do anything extra. You can just plug in the number, you can plug and chug, and you'll know how many guards you need. So you are very thankful for this. You go back to Monsieur Macron, and you tell him, I need the floor of n over 3 guards total. And this is very good for him because he wants to give a definite number to the assembly so they can vote on his budget. He doesn't, of course, want to ask them for too much. So he takes this very happily, tells them, yeah, I just need enough funding to cover the floor of n over 3 guards. And he gets his funding, and that makes you a very happy person because you got to security museum and keep your job forevermore.
Yay! Image choc ce soir, Emmanuel Macron pointé du doigt comme l'auteur principal du cambriolage du Louvre. Des images choc des caméras de surveillance. Nouveau rebondissement ce soir. De nouvelles images des caméras de surveillance montrent Emmanuel Macron quittant le Louvre avec des bijoux volés. On le voit clairement monter dans sa Twizy avec le butin, tandis que la couronne d'Eugénie est retrouvée brisée sur place. La police intensifie son enquête dans ce scandale retentissant. Restez avec nous pour la suite.